All right. So we'll now go through reactive chemistry. So reactive chemistry, basically, we need to understand, well, differences between a physical reaction and a chemical, or basically a physical change versus a chemical change.
Yeah.
And basically, a physical change is a rearrangement of the particles. And there's no sort of change of bonds, so no rearrangement of the chemical bonds. Not at the strict sense, all right?
Yep.
And that means there are no new substances formed. So typical example would be like change of state. Now, chemical change, on the other hand, is a rearrangement of the electrons, which necessarily means that the bonds must be broken and rearranged. In a different way. And this necessarily means that new substances are formed. Okay. And so for a physical change, no substance is formed, particles are the same. And you can reverse it by physical methods, and relatively small energy changes involved. Chemical ones, on the other hand, new substances is formed for sure. New particles are formed, right?
Yes.
The process might be possibly reversed, but definitely not in a physical way. And the energy changes are relatively larger than the physical changes on average. And you might be looking for certain signs. So these are not necessarily true. They don't guarantee it, but signs could include things like, evolving gases. So just typing it out. So signs of chemical reaction could include formation of gas, bubbles. It could include formation of precipitate. It could, for example, see a change in color. Although that's not 100% guaranteed, but that's very possible. You could have a significant change in temperature. And again, that doesn't guarantee it, but it's something to look out for.
Yeah.
You could also look at, for example, disappearance of a solid. But again, usually as distinct from just mere dissolution. So as I said, these later ones are kind of just, things that you might look out for, but they might not be as clear-cut and as clear, and odor is produced. And the reason for that is because maybe it suggests new substance produced.
Yeah.
Or gases. So those are signs of a chemical reaction. Now, we'll talk about the different types of chemical reaction. So your types of chemical reaction. You'll need to know how to classify them.
Yeah.
But number one, synthesis. And basically, it's just a situation where two elements combine together. So, for example, A plus B to give you AB. So that's the general gist of synthesis. And we could take something like, 2Cu plus O2 to give you 2CuO. Now, you also have what's called decomposition, which you can think of kind of as the reverse. So basically, this is where you have something like xy, and it becomes x plus y. Now, it doesn't have to necessarily be that, but more importantly, it's a compound, being broken down into simpler substances.
Yep.
So what you do have to have is one thing on the left and more than one thing on the right. Okay, and that could take all sorts of forms. So you could, for example, have silver chloride to form 2Ag solid plus Cl2 gas, or you could, for example, have calcium carbonate to become calcium oxide plus carbon dioxide gas. But basically, there's one thing on the left and then more than one thing on the right.
Yep.
And this is the process of chemical decomposition, of breaking down a compound into simpler substances, which could ultimately get you to your elements.
Yep.
Thirdly is combustion reaction. And a combustion reaction basically is a reaction with oxygen. And, it is generally exothermic. So that includes things like metals that combust. So we might use something like magnesium plus oxygen to give you 2 MgO. And that counts as combustion of magnesium. But more typically, we might talk about combustion of fuels, like a hydrocarbon. And a typical example is H8A18 being octane plus oxygen. And it'll give you carbon dioxide and water under what's called complete combustion. Now, some students have trouble with balancing these, but it's actually really easy. First job, balance the carbon. A carbon on the left. So that means you've got carbon dioxide only. That means this has to be 8, no questions asked. 18 hydrogen on the left. Well, you've only got hydrogen in the water. So that means you must divide 18 by 2. That gives you 9 as your answer there. Again, no questions asked. And there's no other possibility, really. If this to that has to be a ratio of 1 to 8, and this to this has to be a ratio of 1 to 9. There's just no other way around it. Having said that, though, obviously not everything is done yet. We still need to balance oxygen. And we just count up oxygen. So 8 times 2 is 16 plus 9. That means I need 25 oxygen, which means I need 25 over 2 oxygen here. And now it's balanced.
Yeah.
Now, if your teacher says that you can't use fractions, which I guess some teachers might say that, then you just multiply everything by 2.
Yeah.
If you feel like it, to get your final answer. Otherwise, you can just leave it with a fraction. But the point is, balancing is really simple. Balance the carbon, balance the hydrogen, then balance the oxygen. And then if there is a fraction, then just get rid of the fraction by multiplying if you want.
Yeah.
Now, there is also such a thing called incomplete combustion. And incomplete combustion is, well, more unpredictable. But what we can guarantee for incomplete combustion is that it results from not having enough oxygen. So, for example, this was 25 over 2 oxygen. And I'm going to say that, okay, let's say that's 12.5. So let's say I only have 10 oxygen. So the point is, there is insufficient oxygen for complete combustion. We can guarantee that.
Yeah.
Once you have that, then I can also guarantee on that right-hand side, your products will not purely be carbon dioxide and water. It could be any mix of carbon monoxide plus carbon dioxide plus water. It could be any mix of those, all right? So it's not as predictable. This carbon is your soot and your smoke. Having said that, you know, if you're asked to write a incomplete reaction, as long as it balances out on the left and the right, then you're okay. For simplicity, I'm going to change it so I don't have all three. I've got 10, which is a decent amount of oxygen, just, you know, a bit lower than 12.5. So I'm going to assume that I don't have any carbon to keep things easier. But of course, I can't guarantee that. But this could conceivably happen. And what that means now is hydrogen is easy to balance. I'm going to put a 9 in front of that hydrogen. And then at this point in time, my hydrogen is balanced. Now I know I've got 20 oxygen, but I've used up 9 already, which really leaves me with 11 oxygen to split amongst these. And I have to have 8 carbon if I assume I've only got these. Now, you can go and solve for it if you like, formally. You'll probably find that that will give you the answer. But basically, you know, if you think of this as X and you think of this as Y, then basically you know that X plus Y must equal 8 for the carbon. And you know that X plus 2Y must equal 11 for the oxygen. And you solve those simultaneously, basically.
Yep.
And that gives us our answer for that incomplete combustion over there.
Okay.
We also have what are called precipitation reactions. And these are quite simple. A precipitation reaction simply means you have formed a precipitate. Now, what does that mean? Well, that means you take the solution 1, usually aqueous, and usually ionic, plus aqueous, again, usually ionic, solution 2. Both of these are soluble, right? Both of these are solutions.
Yeah.
But when you add them together, you form what's called a precipitate plus, well, an aqueous ionic solution 3. And this precipitate will therefore be a solid. In other words, you mix 2 solutions together and then a solid comes out very quickly.
Yeah.
Now, this is because you've got AB plus CD, and we'll say A is the positive and B is the negative. And we'll say C is the positive and D is the negative.
Yeah.
And when you mix them all together, what that really means is you get this jumble, once you mix them all together, of A's and C's doing their own thing, unrelated to each other, and D and B's doing their own things, etc. And we know that AB is soluble, so A and B won't become solid, and C and D meeting together won't become solid. But since they're all mixed together, that means A can now meet with D, and B can now meet with C.
Yeah.
So really your question is BD or AC soluble in water? And if your answer is yes, both are soluble, then there's no reaction. But if the answer is, you know, something is insoluble, then you have a precipitation reaction. So for example, let's say AD is insoluble. That means you'll get AD. When A and D meet, you'll get your precipitate.
Yeah.
And then you're left with BC, which is your solution. So actual examples of this might be something like, you know, copper nitrate, plus potassium hydroxide. Both of these are soluble, but when you mix it, you'll get copper hydroxide, which is a blue precipitate, solid, plus potassium nitrate, as an example. And really, for you to determine this, basically you need to be able to determine if your ionic substance is soluble or not. And that relies on you knowing your solubility rules. So to know your solubility rules, what you would then require to do is make sure that you know, firstly, in doing in sort of as a flowchart kind of way, all of these are soluble.
Yeah.
In other words, if you see a group 1, in particular, the most common, sodium, potassium, being the important ones, as well as ammonium, acetate, and nitrate. If you see one of these, you know that it's soluble. Now, once you've determined that, the next thing that you would consider is all halides. So when we say all halides, we are kind of ignoring fluoride here. And usually you're tested on chloride, but it does apply to, you know, the other halides, so bromide and iodide. For year 12, you'll know for bromide and iodide, but in year 11, usually we're just talking about chlorides really. They're soluble, except for when they're paired up with silver or lead. So in other words, I'm saying iron chloride, no problem. Copper chloride, no problem. Potassium chloride, no problem. Silver chloride, okay, exception. Solid, insoluble. Lead chloride, insoluble. Yeah.
Yeah.
We will then also say that all sulfates are soluble, except, and the key ones you would accept are barium and calcium, but we would also add silver and lead to that list. So there is actually a third one here and a third one here, but those are not commonly tested, so I'm leaving them out.
Yeah. Okay.
Now, we will then kind of flip it a little bit here. And this is starting to get a bit borderline, but at this point we would say all hydroxides are insoluble. So not soluble, but insoluble. So we're kind of going the other way now. So they're insoluble, except, and ironically, barium, followed by calcium. So, and this is kind of, well, this is relatively insoluble. So all of these are not very soluble, honestly. All hydroxide are not very soluble, but if you had to find one that was outside of the group 1s and ammonium, then barium is the most, and calcium's really not that soluble, honestly. And at this point in time, if you haven't identified it, then else assume insoluble. Okay. So if you haven't worked out if it's soluble or not at this point, then you say it's insoluble.
Yeah.
So, for example, let's say we've got zinc chloride, which is aqueous, and we're going to add silver nitrate. Then you're going to get silver chloride, solid, plus zinc nitrate. Okay. And that would be what's called your overall equation.
Yeah.
Then you can have what's called the full ionic equation. Make sure you know how to write that, which in this case will be Zn2 plus 2Cl negative aqueous plus 2Ag plus aqueous plus 2NO3 minus aqueous, and then to give you 2 AgCl solid. You don't separate it because it's solid, and then plus 2 Zn plus 2NO3 minus aqueous. But of course, given the fact that you can see that you've got what are called spectator ions on the left and the right, like here and here, as well as here and here. These are called spectator ions. As a result of that, you're going to get your net ionic equation, which is going to be simply Ag plus Cl minus to give you AgCl. And we would apply that concept to our acid reactions as well. So note that you've got three main types of acid reactions. You've got acid plus base to give you salt plus water. This is called neutralization. And this is an exothermic reaction. Now, the net ionic equation for that is H plus plus OH minus to give you H2O. Now we also have the reaction of acid plus metal to give you salt plus hydrogen gas. Again, exothermic, which means basically you've got H plus plus some sort of X metal, and you'll get sort of something like X plus H2 gas. So something like that, for example. It depends a little bit on the metal, about the ratios, but the idea is the same. And then you also have acid plus carbonate, which gives you salt plus carbon dioxide plus water. So that gives you 2H plus plus CO3 2 minus to give you, well, H2O plus CO2. So those are acid reactions. Recognize that this is actually a displacement reaction. So you need a displacement acid. And very similarly, along the same lines, we have what are called metal displacement reactions that occur. So your metal displacement reactions basically occur due to your metal reactivity series. So your metal reactivity series essentially refer to the fact that your metals react. So basically, your general kind of rough idea is you've got your group 1 metals, such as K, Na, La, and then your group 2, so like your barium and calcium. And then, you know, maybe magnesium, then maybe group 3, like aluminium, and then sort of your reactive one, like zinc, iron, roughly. And then, you know, your less reactive ones, kind of like tin, lead, copper. And then further down that sort of spectrum, you've got your essentially inert ones. And those would be like your silver, platinum, gold. And so on this side of things, it's more reactive. On this side of things, it's less reactive. And remember that your metal displacement reaction can have a more reactive metal in solid form, plus a less reactive metal solution in aqueous form. And the two will swap places, and you'll get the more reactive metal solution plus the less reactive metal, which means you'll have something like magnesium plus zinc nitrate. They'll swap places and you'll get magnesium nitrate plus, I'll make it more obvious, but yeah, zinc shouldn't be as reactive anyway, but I'll make it more obvious, plus copper solid. And that's your metal displacement reaction. Noting that that actually makes it a redox reaction. So remember, redox reactions are composed of reduction and oxidation. So oxidation is loss of electrons. Reduction is gain in an electron. So if we're taking an example like our electrochemical reaction just then, that means the oxidation that actually happened is the magnesium became Mg2 plus 2E minus. And the reduction that occurred was copper 2 plus 2E minus to become copper solid. And then you basically look up your reference sheet for the relevant E0 values here. And once you have the relevant E0 values, that gives you, well, basically whether this reaction will occur or not. And that will tell you the voltage of this cell. So if we take a look at the reference sheet, so you can see here, this is our reference sheet.
Yep.
And if we take a look at this reference sheet, then we can see that your magnesium over here is negative 2.36 for the reduction, but what that therefore means is that the Mg solid to Mg2 plus 2E minus will be positive 2.36 volts. And then your copper is down here. And so that would then mean that your copper 2 plus 2E minus to give you CuS is positive 0.34 volts, giving you a total and your net equation of Mg solid plus Cu2 plus to give you CuS, Mg2 plus, and that will give you a total of 2.70 volts. Just noting, of course, that this is a reduction table. So what that means is the further down you go, the more it wants to reduce. And anything that reduces causes something else to oxidize. So these are stronger oxidizing agents at the bottom.
Yeah.
And anything towards the top doesn't want to reduce. Instead, it wants to oxidize. And if it wants to oxidize, that means it will reduce others. So these are strong reducing agents, otherwise known as reductants. Strong oxidizing agents are also known as oxidants.